Okay, I think we'll get started. If you're coming from the G&L project, I encourage you to look at the introduction video to this playlist to make sure this is the right course for you. Otherwise, we're going to talk about torque today. And so we're starting to see, when we've talked about rotation, these analogous properties to the linear case. So we had angular position, angular velocity, and angular acceleration. Well, torque is going to be the rotational analog of force. So force will act to accelerate an object in a linear direction. Torque will act to rotate an object or to accelerate an object in a rotational direction. Okay, so let's take an example of something that I'm sure you're familiar with. If we've got this wrench here, we want to undo this bolt. Well, we could go in with our thumbs and fingers and try to unscrew it, and we probably wouldn't be able to unscrew it. So we take a wrench and we try, and maybe we can't maybe we can't get it, so we get a bigger wrench, one with a longer arm. So we have some life experience here with this idea of how our device for trying to apply a force is impacted by the distance from that rotational point. So let's put that together in a more formal way with this idea of torque. So if we look at our bolt here, it's going to rotate about the center, and we call that a pivot point. So let's put that point down here. This is point P, pivot point. And then we have a distance from that pivot point upon which we're going to apply a force. Right? So if we apply a force in this direction at this point, we have a certain distance r to the pivot point. So that's called r. Now, in general, we might not apply the force perpendicularly. Your life's experience tells you that if this is the wrench, you don't apply your force this way, right? The best optimal way to do it would be to apply perpendicular. If you want to tighten it, you go up. Loosen it, you want to go down. Well, that is definitely true. That's the optimal way. You get the most of your force is acting to turn this wrench. But in general, our force might go off in some direction. And what we need to do then is, based on the arm, right, we run an extender out this way. So this is our distance r. I suppose make that a little more clear. This is our distance r. We extend this line out this way, and then we draw a perpendicular as well, and we figure out the components of this generally, force in some general direction, and we figure out the force in the direction perpendicular to this radius and parallel to that radius, or perpendicular to this arm and perpendicular to this arm and parallel to this arm. Only the perpendicular part of the force, or the perpendicular component of the force, will initiate rotation or contribute to rotation. The parallel component won't do anything regards to rotation. Okay, well, this rotational force, and it's not a force here, I put it in quotes, it doesn't have units of force, but it plays the role of force when we're talking about a rotation. So this rotational force is called torque. And we define the torque vector as a magnitude and a direction, and by direction we mean which way is it trying to rotate. And the convention in the book that's being used for this course is that rotation in the counterclockwise direction is positive, and in the clockwise direction is negative. So the counterclockwise direction positive, clockwise negative. Well, based on what we said here, the torque is, we can define this torque as this arm, right, and the perpendicular force. So let's kind of make sure this makes sense, right? We grab a longer wrench if we want to have a better chance of undoing that bolt. The reason we want a longer wrench is because we're able to apply more leverage on that pivot point. So the arm is certainly going to matter. And then how much force we apply in the perpendicular direction is going to matter. Now, it's not intuitive that they would be linear necessarily, but they are. So r to the first power and force perpendicular to the first power. So that's how we kind of took our intuition about this wrench and how it works and defined this quantity torque. Now, sometimes we want to work with the force itself, not the perpendicular components, and then a piece of the part of the arm that contributes to the rotation. So it's shifting this contribution to rotation from the force to the radius, and this is less intuitive. So we define this so-called lever arm as r perpendicular. So let's see how that works. So let's take this same picture now and put our force off in this direction. We define this angle based on this extended line, so we still extend this line segment, and of course by just simple geometry, these angles are equal. And what we do then is we draw the perpendicular, and we define the lever arm as as this distance here, perpendicular to the force direction. See, it's just kind of switching the roles of force and direction. And in that case, we get r sine theta. So torque, let's write it up here. Torque is going to be equal to r sine theta, then the total force. So this is the magnitude of the torque. And that's the magnitude of the force there. And then we have to decide which direction is it going. So if we look at the torque and it's going to move it in the counterclockwise direction, then the direction is positive. The clockwise direction will be negative. Okay, so let's do a little example here. Let's say we have a 10 Newton force applied at a 60-degree angle. I didn't quite draw that right. So let's imagine that's a 60-degree angle. And we have a total radial arm here of 10 centimeters. Okay? Well, the radial, or the lever arm then, is going to be r, which is the 10 centimeters, times sine of the angle. And so that's going to equal this. You can check that on your calculator. And then our torque is this, so this is sine of that angle, and then times the magnitude of the force, say 10 newtons here in this example. So we get the magnitude as 0.87 Newton meters. So here's the units, and Newton meter is for the force, the SI units for the torque, the torque. And then we have to decide, okay, looking at this picture, this is going to contribute to a rotation about this pivot point in this direction, so in the clockwise direction. So that's going to be negative. And so because it's clockwise, it's a negative 0.87 Newton meters. Okay, well, let's jump a little bit to a different topic, but it'll come back here at the end. That's this idea of center of gravity, or center of mass, sometimes it's called. So let's imagine we have an array of point masses. So point masses here. And I'll just draw 3 of them, but imagine we could have any number of them, 17 of them if we wanted. Well, each one of these is going to have a mass, right, at a point, and the point will have an x value and a y value. So mass 1 at x1 and y1, and so on. So we determine the center of gravity of this, or center of mass of this system, by this calculation here. We leverage the position by the mass, and that should make some sense. If this point mass is going to contribute to the overall center of mass, and it's really heavy, right? That's going to make that point more important than if this point is really light. So if this is a really heavy point, this is a really light point, the center of mass is going to be drawn closer to the heavier mass. So we leverage both the X and Y components by mass 1, by mass 2, by mass 3, 4, 5, 6, all the way out. And then we have to divide by the total mass. So M1 plus M2 plus M3. And that gives us our X and Y positions. Okay, so pretty straightforward calculation. If there's a lot of points, it can get a little bit messy, but very easy to follow this formula. Just practice a little bit by plugging in some values. Now, what if we have an extended object, and if it's just some general shape, then we need some calculus, and of course this is a non-calculus based class, so we can only do some special cases. And one special case is when we have a uniform extended mass, and that's a very common case. So like a steel beam, for example, would be a uniform mass. So what we can do is this will behave in a center of mass type setting as if you can collapse the whole thing right down to the dead center of it and place the entire mass right there. So let's say this was a 1 kilogram bar. If this is the length of it, we'll call that D, and it's 1 kilogram bar, we would say it's equivalent to a point mass at D over 2. So it'd be like having 1 kilogram at, and let's say D was 1 meter. It would be like having 1 kilogram at half a meter. Okay, so let's look at some situations where we might now bring in some ideas from torque. So let's say we've got this metal rod, and it's attached here to some kind of stand, and it can swing back and forth like this. It sort of as a solid pendulum. So if we position the mass right here, so let's just freeze time right here. We'll draw a free body diagram for this. Well, this isn't really a full free body diagram, but we would imagine here now we've got a weight force pointing down, and we can position that weight force at the center of mass or the center of gravity. So again, if this were a 1 kilogram bar and this was 1 meter, this would be the same as having a point mass at 1 or at half a meter here, and then this angle. So if we can collapse that to a single point. And now let's imagine, in terms of calculating the torque, we've got a weight force of W, so we're going to need that perpendicular weight. And so if this is some angle theta, then, and this is some length D, then our torque is going to be D over 2 sine theta, and then mg, where m is the mass of the whole bar. And then the direction here, so this is the magnitude, and then the direction would be, in this case, clockwise. So we can either write clockwise there, or we can put a negative sign. We could have an elaborate piece like this. With something like this, what you can do is treat it as two beams. Let's say this one's a little bit longer than this one. And if this is the pivot point right here, we kind of can imagine that that's going to want to swing down this way. And we can see that because for this bar that's hanging vertically, the weight force is straight down the length of this, or the radial direction. So it contributes nothing to rotation. It's not trying to rotate in either direction. But for this bar, the weight is exactly perpendicular. So it's contributing all the weight to the torque. And so we're in a setting right now, at least if this was frozen right here, that we're going to have some torque that's going to want to rotate that whole system this way. Now, as it does that, as this swings down, this guy will kick up and want to rotate back that way. And so it'll end up in some equilibrium position, probably almost at 45 degrees. But if this bar is a little bit longer, then, maybe that would be 40 degrees and this would be 50 degrees or something like that. Okay. All right. So that's an overview of torque. A couple of big pictures here now. Torque is going to play the role of force for rotations. So we'll start to accumulate more and more analogous properties for rotations, and we'll eventually have everything that we do in linear space now in rotational space. We have one more thing to do, which is grab what's called the moment of inertia, which we haven't talked about yet, and then we'll be there. We also talked about center of gravity, kind of a separate point, but valuable in doing things like this. So make sure you also review that.